In this video, we're going to go over the mechanism of acetal formation and also discuss how this mechanism is reversible. The first step in this reaction mechanism involves using the proton. Now remember, anytime that you're about to start a mechanism and you have no idea what to do, always ask yourself what you do know about the compounds that are present. And what you do know about acidic conditions is that their goal in life is to try and protonate something. So your first step when you see acid should always be to protonate something. So in this case, that something is our carbonyl. So we are going to pick up that proton, and notice we're going to use reversible arrows for every step of this mechanism because this mechanism is reversible. And now we have a hydrogen attached to the oxygen. Every time you draw a new structure, also do a little accounting and make sure that you have exactly the right structure. And what I mean by that is we took a pair of electrons and we created a bond to a positively charged atom. So we took a neutral and a positive together. That means our next structure should be positive. So our oxygen still has one lone pair, but it lost one of them to the bond to the hydrogen, which makes it positively charged. There's also a resonance form here that's really special to us because it shows us a pretty big hint as to what can happen next. So the pi electrons in the carbonyl bond can get pushed up onto the oxygen. Giving us a single bond between the carbonyl carbon and the oxygen. This also means that there are two lone pairs on the oxygen again, but where does the positive charge go? Well, we took the electrons away from the carbonyl carbon, so the positive charge must be there. Now, I said that this step, or this resonance form, would give us a hint as to what the next step was. And that hint is the positive charge on the carbonyl carbon. We know that our ultimate goal is to put on two ethoxy groups, and that we're eventually going to be displacing the carbonyl oxygen entirely, and it becomes part of the water molecule. So that means that the ethanol molecules have to somehow attach to the carbonyl. And this is where we're going to start making that happen. So we have a molecule of ethanol, and there are two lone pairs on the oxygen atom. It's going to attack the carbonyl carbon. And that gives us our next structure. So now that we're here, we want to do some of that accounting again. There are two lone pairs on this oxygen. There is one lone pair on this oxygen. The other lone pair from the ethanol oxygen is part of the covalent bond. So that means that there is a positive charge here. Now, before we move forward, we want to think about whether or not this is a stable structure. Does oxygen like to be positively charged? Hopefully what you're thinking is that oxygen is a very electronegative atom, so no, it does not like to be positively charged. So we want to deprotonate it before we move any further. And we have an excess of ethanol, so we're going to use ethanol to deprotonate it. And so we're able to give the electrons back to the oxygen. Does this structure look familiar to us yet? This is our Hemiacetal. This means that we are halfway through the mechanism and we are halfway to the acetal. So let's do a little bit of thinking here. We know that in order to get to the acetal, we need two equivalents of ethanol. We no longer have this, carbonyl resonance form that we used earlier, right? So how are we going to make this carbon free for an attack from another ethanol molecule? And we know that somehow this oxygen has to leave. It's going to be part of the water molecule. That is our carbonyl oxygen. And the way that we're going to accomplish that is to protonate it and turn it into a good leaving group. This is a trick that you learned back when you learned about dehydration of alcohols. And fortunately, we have acid around, or you can take it from your protonated ethanol. Doesn't really matter. If you just want to draw H+, that is fine by me. Okay, remember to check your charges. You went from something neutral and a positive species to something that has this one lone pair on this oxygen. So there must be a positive charge on this oxygen, which is perfect. That's how we want it, because now we can see why this is a good leaving group. So the water molecule is going to leave, and it's going to take the electrons in this covalent bond with it. And this gives us a new carbocation, which we can easily attack with another molecule of ethanol. Now we're almost there. The only difference between this structure and our target structure is a single positive charge. How do we get rid of that? Well, you can use some of your ethanol, you can use some of your water lying around. There's a lot more ethanol, so that's more likely, plus it's a little more basic. But we can take a molecule of ethanol and deprotonate it, and that gives us our acetal. So I really enjoy this mechanism because I just think it's really elegant. It doesn't look like it so much on this slide. It looks a little messy, but there are a lot of steps here that really just make a lot of sense if you just keep asking yourself questions. So we kept, putting on protons and creating positive charges, and then we would remove the positive charge somehow. So if the positive charge was the result of a proton, such as here, we deprotonated it. If the positive charge was a carbocation that resulted from resonance or from a leaving group leaving, we fixed it by attacking that carbocation with a molecule of ethanol. So anytime that there was something displeasing or unstable, we were able to stabilize it in a logical way. And so this mechanism is actually 100% reversible using the exact same logic. If we want to get rid of these ethoxy groups and return to the ketone, we're going to have to make them leave sequentially, and we're going to have to use water to recreate the carbonyl. So you have to think about the conditions that you're going to need. If we're going to reverse it, you can't just do it in acid. You're actually going to have to reverse it in aqueous acid. And this makes sense because in order to make it, we had to do it in ethanol and water, ethanol and acid, and we produced a molecule of water. So if we want to go back towards our starting materials, we can use Le Chatelier's principle and add in a ton of water to push us towards our reactants. So you want to use aqueous acid. And then as you go through this, the steps read just the exact opposite of what we just did. I want to get rid of an ethoxy group. Well, I should protonate it, and then it would be able to leave and give me this carbocation, which I could then attack with a water molecule to get this structure. And then I could deprotonate it to get to my hemiacetal, and so forth. A really good practice for you would be to draw out the reverse mechanism.